Now, this bit of Lego here is going to represent a white dwarf. And basically, for a low mass star, at the end of its life, it becomes a white dwarf. And basically, you've got a force which is pulling inwards due to gravity, the fact that there's, things which have mass, everything kind of pulls in. And there's also an outwards force, okay? Now, when a star's in a main sequence, the force of gravity is balanced by the radiation pressure pushing out from all these fusion explosions. But at the end of this life cycle of a low mass star, there's no fusion happening inside. And this outwards force that's counteracting gravity is what we call the electron degeneracy pressure. And this is really caused by the fact that we have electrons which are basically being pushed together, and two electrons can't exist at the same point. So as these get closer and closer together, there's going to be a force of repulsion between the two. And this is kind of what stops those stars collapsing anymore. But in high mass stars, what we find is that there's a point where the force of gravity pulling in is bigger than this electron degeneracy pressure. And basically, when you have stars which have a white dwarf, so this is the core left, which is greater than about 1.44 solar masses, suddenly this white dwarf can't exist anymore. And this is a limit, and we call it the Chandrasekhar limit. And so basically, this video is about things that at the end of their life have the mass of the core of the star which is left as greater than 1.44 solar masses. And this is the point at which gravity, which is bigger than this electron degeneracy pressure, it kind of sort of takes over. And eventually what happens is all sorts of weird stuff where electrons and protons get pushed in to make neutrons. And this is what we're looking at when we look at the life cycle of a high mass star. So these high mass stars, which tend to be greater than about the mass of sort of 10 solar masses, or 10 times bigger than our sun, they're made up of a huge amount of stuff. For that reason, the force of gravity pulling all of this stuff in is very big. And for this reason, inside the actual star itself, the temperatures are really, really high. And this means that a huge amount of fusion occurs. And for this reason, the radiation pressure, sort of the gas pressure pushing outwards, is also really high. And it's these really high mass stars with a lot of stuff that actually burn up that hydrogen really, really quickly and have a very kind of low lifetime. Now, basically, towards the end of their life, because they're burning their fuel so rapidly, what happens is, just like in a low mass star, the hydrogen starts to get used up as we start to make things like helium. And as time goes on, the force of gravity pulling everything in is really, really high, but maybe this force here gets a bit smaller. And what happens then is that this star swells into a red supergiant, also called a super red giant. And it's this phase of the star which is really, really interesting. So this red supergiant is immensely big. The atmosphere that's swollen up is just enormous. And in this atmosphere, what we have is, a lot of kind of sort of the hydrogen. And, because, let me just put the hydrogen out there. But it's really what happens in the centre which is really important. The kind of central core of that star collapses. And here, as it collapses, what we find is that the temperature rises up a huge amount. And effectively, this allows not just the fusion of maybe hydrogen to hydrogen, but also helium to helium. And what we then get is a load of other elements which are then formed. So maybe helium starts to make things like perhaps some carbon. We get things like, neon, oxygen. We get magnesium, silicon, and there's all of these different sorts of elements which are being fused together. Now, I'd like you to imagine effectively the inside of the core, here we go, of that kind of massive super red giant is a bit like the centre of an onion. What we have are different layers, and as we have heavier and heavier elements being fused together, we get deeper and deeper into the centre of the core. But what we have in the very middle is we have things which fuse together to make some iron. Now, iron is the kind of the most stable element, and iron will not undergo fusion to make anything heavier than that. So effectively what we have inside the centre of this, the core of this kind of super red giant, is the fusion of heavier and heavier elements. And you might be familiar with this diagram here, which shows the binding energy per nucleon versus the proton number. So basically what we find is that iron is the most stable element, and that's what everything else wants to become. So how do we get these heavier things here? Well, basically, there's going to be some point towards the end of the life when we start to run out of all the elements that we need to actually fuse together. And at this point, the force of gravity pulls everything inwards. And what happens is is that effectively all of the elements in that star come together, and what happens then is that the outer layers bounce off the central part, and we have a supernova. And a supernova is when the outer parts of that super red giant, they all collapse, they bounce off the core, and then they get ejected out into space. And what happens at some point in this time is that we start to make all of the heavier elements, things like the kind of copper, these sort of heavy metals, things like the uranium. Anything which is heavier than iron can only have been made in a supernova. And often this is categorized as a type 2A. So basically, or even just a type 2. So basically this is the kind of supernova that occurs. And, the stuff inside your body, a lot of the stuff inside your body can only have been formed in the fusion that takes place inside a high mass star and inside that supernova, which is pretty incredible. Now, basically, what gets left behind is a kind of a super kind of dense core. And effectively, if the core that's left behind, bearing in mind most of the matter has been ejected out into space, if the core is greater than about 1.44 solar masses, remember this is a Chandrasekhar limit, what we then get is something where all of the electrons start to get pushed inside all the other kind of particles within inside the centre of that star. And effectively, if you have a proton which is +1 and a negative electron which is -1, if you push these two things into the same place, what you then get is a neutron. And I think we've seen some similar equations to that when we've looked at sort of beta minus and beta plus decay. So effectively what we make then is what we call a neutron star. Effectively all of the things inside that star, all the protons have been pressed into all the electrons just to leave neutron after neutron after neutron. And this is basically one massive nucleus of an atom. So this neutron star has a density of about, roughly about 10 to the 17 kilograms per cubic meter. A teaspoon of this stuff will kind of weigh the same as like a massive sort of ocean-going liner. And some of these also rotate. We've basically taken the mass, something which is really big and rotating. It's become incredibly small, but it's still rotating. And in order to conserve angular momentum, these things spin really fast, perhaps many times per second. And what we then get is something that we call a pulsar. And as it rotates, it gives out a load of energy. And these are really interesting kind of stellar objects. However, what happens if the mass is particularly big? What happens if the mass is greater than about 3 solar masses? Well, effectively, the only force pulling everything in is gravity. And, there's kind of things like the kind of strong force which stop these two things pushing together. But we get to a point where the force of gravity is so strong that the neutrons are pushed inside other neutrons. And then eventually, at some point, all of the mass of that star tends towards what we call a singularity. The only force is basically gravity pulling everything in. And this is where we get into the realms of things like a black hole. And this is where the physics that we do at A-level stops working. Do you remember that there's things like sort of Newtonian mechanics that says, things like the force due to gravity is equal to minus gmm over r squared? Well, there's a point where effectively r is equal to 0, and therefore the force should equal infinity. Can that work? Well, it doesn't really work if we look at Newton's laws of gravity. And a black hole, these are really fascinating things. And these are caused when really supermassive, stars actually kind of end their life. And this is kind of where our normal kind of physics breaks down. And that's why things like LIGO, gravitational waves, the kind of latest advancements and the kind of things that people like Stephen Hawking kind of talk about, that's where all of that comes in. And I've put a few links in the video below that kind of explain a bit more about that. So, a high mass star. It burns really hot, has a short lifetime, becomes a super red giant, it supernovas, leaving behind either a neutron star or a black hole. I hope that makes sense. Thank you very much.